The next major bottleneck in artificial intelligence may not be the processor. It may be the tiny metal connections carrying data between processors. AI systems are becoming so large that thousands of chips must work together as if they were one machine. Every chip constantly sends and receives information. The faster the model grows, the more data must move across servers, racks, and entire data centers. That movement consumes enormous amounts of electricity. It also creates heat, delay, and physical limits that cannot be solved simply by manufacturing a faster GPU. Now the United States is investing hundreds of millions of dollars in a different solution, replacing some electrical connections with light. The U.S. Department of Commerce plans to award GlobalFoundries $300 million to advance silicon photonics and co-packaged optics. The goal is to build faster, more energy-efficient links for artificial intelligence data centers and strengthen domestic production of the technology. This may sound like a specialized semiconductor project, but it addresses one of the most important problems facing the AI industry. Modern AI depends on moving data as much as calculating it. A single accelerator can perform trillions of mathematical operations, but it cannot work effectively if it spends too much time waiting for information to arrive from memory or another processor. When thousands of accelerators train one model, every delay is multiplied across the system. Imagine thousands of workers assembling one enormous machine. Each worker may be extremely fast, but the entire factory slows down if the parts cannot move between stations quickly enough. That is what happens inside an AI data center. The chips are the workers. The communication network is the factory floor. Traditional computing systems move information using electrical signals through copper connections. This technology has supported computers for decades, but it becomes increasingly difficult at the scale required by modern artificial intelligence. Electrical signals lose energy as they travel. Faster connections create more heat. Longer distances require more power. When thousands of processors communicate simultaneously, the networking system can consume a significant portion of the data center's total electricity. Silicon photonics approaches the problem differently. Instead of sending information only as electrical signals, it converts data into light and moves that light through optical connections. Light can carry large amounts of information rapidly while using less power over longer distances. Fiber optic networks already move internet traffic around the world. Silicon photonics brings similar optical principles directly into semiconductor systems. The word silicon is important because the optical components can be manufactured using processes related to conventional chip production. Engineers can build lasers, modulators, detectors, waveguides, and electronic control systems into compact packages designed to operate beside processors. The U.S. funding will also support co-packaged optics. Today, many optical network components sit at the edge of a server or networking device. Electrical signals must travel from the processor across the circuit board before reaching the optical connection. That journey creates power loss and limits speed. Co-packaged optics moves the optical components much closer to the processor. Instead of sending electrical signals across a longer board, the system converts them into light near the chip. The shorter electrical path reduces energy consumption. The optical connection then carries data more efficiently through the rest of the system. This becomes especially important in rack-scale AI platforms. Companies such as NVIDIA and AMD now design complete racks containing dozens of tightly connected accelerators. Multiple racks can then form clusters with thousands of processors. The performance of the entire system depends on how quickly those processors exchange information. During AI training, different chips may process different parts of the same model. They constantly synchronize results, transfer model parameters, and exchange intermediate data. If communication becomes too slow, adding more GPUs produces diminishing returns. The company pays for additional chips and electricity, but receives less useful computing performance from each new processor. This is sometimes described as a scale-out problem. An individual chip may become faster every generation, but the system cannot scale efficiently unless the network improves at the same time. Global Foundries says the new project is targeting transfer speeds of 400 gigabits per second and energy efficiency up to 5 times greater than current implementations. Those targets matter because electricity is becoming one of the largest constraints on artificial intelligence. Technology companies are planning data centers that require gigawatts of power. New projects increasingly depend on long-term energy contracts, new transmission lines, natural gas plants, nuclear power, and renewable energy facilities. Every watt saved inside the networking system reduces both operating cost and cooling demand. The issue is not only the electricity used directly by a connection. Nearly all electrical energy consumed by computing equipment eventually becomes heat. That heat must be removed using fans, liquid cooling, pumps, chillers, and other infrastructure. Reducing the energy consumed by data transfer can therefore create savings across the entire facility. Faster optical communication could also change how AI systems are physically designed. Today, processors must often remain relatively close together because electrical connections become less efficient over distance. Optical links could allow companies to connect computing resources more flexibly across racks or sections of a data center. That may make it easier to build larger clusters without suffering the same communication penalties. It could also improve how expensive hardware is shared. A data center might separate processors, memory, and networking resources, then connect them optically as needed for different workloads. Instead of every server containing a fixed combination of components, infrastructure could become more modular. This concept is sometimes called disaggregated computing. A company could assign more memory to one task, more accelerators to another, and reconfigure resources through the network. Optical connections would help make those remote components behave more like parts of the same machine. The US government sees another issue beyond performance: supply chain control. Much of the advanced silicon photonics and optical packaging supply chain is concentrated outside the United States. Major companies in the field include Taiwan Semiconductor Manufacturing Company and Tower Semiconductor in Israel. Washington has spent years trying to rebuild domestic semiconductor capacity. Most attention has focused on advanced processors, memory chips, and manufacturing equipment. But an AI system depends on many specialized components. A country could manufacture processors domestically and still depend on overseas suppliers for optical links, packaging, substrates, or testing. A shortage in one less visible component could delay an entire data center project. The Global Foundries Award is therefore part of a broader attempt to build more of the AI supply chain inside the United States. The company plans to use the funding for research into new materials and manufacturing techniques. Those technologies could later be produced and packaged at its facilities in New York and Vermont. Global Foundries received a previous $1.5 billion award in 2024 to expand U.S. manufacturing. The new $300 million investment is designed to add research and production capabilities related specifically to optical components. The company argues that it could eventually provide an end-to-end service inside the United States. That would begin with a bare silicon wafer and end with a tested optical module ready for use. This is valuable because packaging has become almost as important as transistor manufacturing. The most advanced AI systems are no longer built as one simple chip. They combine multiple processors, memory stacks, interconnects, optical components, and specialized packaging technologies. A company may design a powerful accelerator, but the product cannot operate at full performance if the memory or communication system cannot keep up. This changes the semiconductor race. For decades, competition focused heavily on creating smaller transistors. Smaller features allowed more computing elements to fit onto a chip. That process remains important, but it is becoming more expensive and technically difficult. The industry is now searching for performance gains from advanced packaging, chiplets, memory design, networking, and optical communication. In other words, the future of AI may depend less on one giant processor and more on how effectively many specialized components work together. Silicon photonics is not a new idea. Researchers and semiconductor companies have worked on optical computing and communication for years. The challenge has been cost, manufacturing complexity, reliability, and integration. Optical components must align with extreme precision. Lasers generate heat and require stable operation. Packaging must protect delicate connections while supporting high-volume production. A technology can perform well inside a laboratory and still fail commercially if it is too expensive or difficult to manufacture consistently. The Global Foundries project will need to prove that these components can be produced at scale with acceptable yields. There is also competition from established suppliers. Companies across the semiconductor, networking, and optical industries are developing similar technologies. NVIDIA, Broadcom, Intel, Cisco, Marvell, TSMC, and several startups are working on optical interconnects or co-packaged systems. The winner may not be the company with the fastest experimental connection. It may be the company that can manufacture millions of reliable components and integrate them into existing data center platforms. Standards will matter as well. AI data centers combine processors, switches, memory, cables, software, and cooling systems from multiple companies. Optical technology must work across those different environments. If every supplier creates a closed system, customers may become locked into one platform. If shared standards emerge, optical components could spread more quickly across the industry. The $300 million award is therefore not simply a subsidy for one chip company. It is a signal that governments now view data movement as a strategic part of artificial intelligence. The first phase of the AI race focused on models. The second phase focused on GPUs. The next phase may focus on everything connecting those GPUs together. As systems grow larger, the processor itself becomes only one element of the machine. Memory, power, cooling, networking, packaging, and optical communication determine whether the full investment produces useful performance. This creates a strange future for computing. The most advanced digital systems may increasingly depend on photons, tiny particles of light, moving through microscopic pathways beside silicon processors. AI was built by turning electricity into calculation. Its next leap may come from turning data into light.